All right, so let's dig into this week's lecture topic material. This week we're talking about syntax coverage. And so where are we on our graph? Well, here we are over on the last topic, syntax. We're going to be looking in class just at applying this to source code, but there's any number of things that you can apply this to. But kind of in keeping with my sort of practical take on the things that we're doing, we're going to be primarily looking at source code. So when we want to do syntax-based testing, we're relying on the fact that the artifacts that we're testing, source code, for example, tend to have syntax rules. And when artifacts have syntax rules, we can use two approaches to develop tests. We can either look to cover the syntax in some way. So if we had some protocol, for example, some message protocol, and the message protocol had 5 operation codes and each of them had 2 arguments, we could start to look at, well, how many arguments are there? And this is kind of an input domain modeling approach, understanding what are all the different combinations that I could do and can I cover all those syntactic variations. The other approach that we can take is to violate the syntax. So what if I have this protocol and I can put together good messages that follow the protocol and send it to my system and make sure that my system behaves properly. But I could also test my system by violating that protocol in some ways, right? By passing it invalid, preferably subtly invalid messages. If I just throw garbage at it, then typically systems are usually pretty good, right? With the slightest amount of effort, you can make your system recognize and reject things that aren't even close to a valid message. But if I give it something that's close to a valid message, can I uncover any unexpected behaviors in the system? Those might be interesting test cases. So one common approach for syntax manipulation is basically the description I was just talking about, is fuzzing or fuzz testing. And in fuzz testing, what we're trying to do is provide inputs to our system that are invalid, but they're pretty close to valid. And what we'd like to do is get these inputs to pass through our input validation for the system to say, oh, that looks like a good, that looks like a good command or a good message. But there are errors in there that maybe our system won't catch. And perhaps we can show that our system will behave in some undesirable way, which will, of course, then give us the opportunity to go fix that. So fuzzing, it might selectively modify the input grammar, or it might use some rules of thumb, right? Some heuristics based on past experience. It may make just simply randomized changes, although random changes aren't necessarily always all that useful. So if we look at an example that's kind of related to fuzz testing, the heartbleed bug that was a big deal a few years ago. Basically, the way heartbleed worked was that what function was it on Linux machines? It was basically it was a query, a status query. You could send a status query, and you could give it a string to return and tell it how long the string was. And so, as in this upper example, you could send in and say, hey, here's a status query, reply with 6 characters of potato, and it would reply with potato. But the heartbleed bug was that it didn't validate that number of characters. So you could do this. You could ask it to reply with a string, but you could give it a number that was much, much bigger, and it would just read out memory and blat it back to you. And so whatever happened to be in memory, could be some interesting things, would just get echoed back to you. So that's an example of testing that's kind of related to fuzz testing, right? We're taking that protocol, we're taking that syntax rule, and that rule that said the number of characters should be the same as what we've sent in. We're violating that rule by asking for more characters to see what happens. And the next type of testing we're going to talk about is mutation testing. And this is what we're going to spend the bulk of our time on this week and next week. And you could view mutation testing as kind of a generalization of fuzzing. But instead of fuzzing data, we're actually going to be fuzzing the syntax of the program that we're testing. So in mutation testing, we're going to take a ground string, some syntactically valid original artifact. So a good message, the original program text, something. And we're going to apply some mutation operators to it. And a mutation operator is just a rule that tells us a way to modify the artifact. So a mutation operator from Heartbleed might say, change the size, right? If it asks for 5, change it to 10. That generates a mutant, right? That modified argument, that modified artifact. So now we have a modified data input or a modified version of the original program or something. And it's either valid or it's very close to valid, right? We're not trying to do random modification because, as I said, that's not usually very interesting or very effective. And then we're going to determine whether using that mutant exhibits the same behavior as the original, as the ground string, or whether it exhibits a different behavior. And if it exhibits a different behavior, then we say that we have detected or killed the mutant. So we can apply mutation testing to lots of things. We can apply it to input grammars, modeling languages, specifications, and most frequently, and what we're going to talk about tonight, we can apply mutation testing to program source code. So mutating program source code, this is the original use of mutation, probably still the most widely known and most widely used application of mutation testing. And generally we're using this at the unit testing level. We're going to apply mutation to individual classes or individual methods in order to test them. So mutation operators are applied to the ground string, which is the original text of our program, to produce a set of mutants or modified versions of our programs. It's important to understand that these mutants are not tests, right? We are not generating tests by applying mutation operators to our original code. What we're generating is mutated versions of our code that might help us develop or evaluate tests. And how do they do that? Well, first of all, we can use mutants and mutation testing to help us develop tests. Essentially, what we're going to do is we're going to create a set of mutants based on our original program, and then we're going to write tests to kill those mutants. In other words, we're going to write tests that will pass on the original program and fail on the modified program. And to the extent that software developers use mutation testing at all, which isn't very much still, this is generally how software developers and engineers use mutation testing. They will generally use it to develop a test set. We can also use mutation testing to evaluate test sets that come out of other processes. So given a set of tests that are developed using some other criterion, how complete are those tests? And this is how software researchers tend to typically use mutation testing. And these two are not, they're complementary. They're not mutually exclusive. So this all seems kind of strange. And the first time I heard it, I was sort of thinking, so I'm taking a program and I'm injecting mistakes into it. And then I'm finding those mistakes. And that's supposed to somehow give me a better program? I'm not sure how that's really supposed to work. So there are two things that underlie this that are kind of the keys to make it work. And the first is the competent programmer hypothesis. The competent programmer hypothesis, how I wish this was always true. Programmers are generally competent. They tend to write their programs in a way that the programs are nearly correct. And I guess, we'd like to think that's true. And the side effect of that is that small changes to programs that are made by mutations are considered to be similar to or reasonable approximations for the kinds of errors that developers might actually make on their own. The second piece of this is the coupling hypothesis. And the coupling hypothesis states that complicated faults are coupled to simple faults, such that if we have a set of tests that finds simple faults, it will tend to find complex faults. In other words, the simple faults that we're injecting with our mutations tend to be useful proxies, right? They tend to cause us to generate tests that are effective at finding real faults, even though the real faults might be more complex. And so understanding those things, it starts to come into focus a little. Oh, all right, I'm starting to see how maybe that would be useful. So let's go through a couple definitions, then we'll dive in. We'll talk a little bit about what mutants really look like and what the process might be for creating them and using them. So we can have several categories of mutants. A mutant can be live. A live mutant is simply one that has not been killed by a test. So there is not yet any test that passes on the original program and fails when run against this mutant. If that's the case, then the mutant is live. Excuse me. A killed mutant or a dead mutant is one that has been killed by a test. I wrote a test, the test passes on the original program, it fails when I run it against this mutant. Therefore, I have killed this mutant. A stillborn mutant is one that's syntactically invalid. It can't be compiled, it can't be executed. So my mutation operator ran and it made some change to my original program, but that particular change is not a valid one, right? It's out of the syntax. So the compiler can't compile, it can't build the program. So that's dead, right from the very beginning. If I can't build it, it's dead and uninteresting. We can also have a trivial mutant. And a trivial mutant is one that's killed by every test that reaches the point at which I've made the mutation. Right? So if I've made a little twiddle to the program down here, any test that reaches that statement where I made the change, if every test that reaches that, if every test that reaches that fails on the mutant, then I have a trivial mutant. Last of all, we can have an equivalent mutant. And this is kind of a weird one. An equivalent mutant is a mutant that behaves identically to the original. There is no possible test that can kill this mutant. Even though it's syntactically different from the original, it is semantically identical, so that it always behaves in exactly the same way. And that seems counterintuitive, because we would kind of like to think, well, there's really one correct way to write a program, and any mistake that I make along the way will cause the program to behave poorly under some circumstances. And that turns out to not be true. And in fact, somewhere between 10 and 20% of all mutants are equivalent mutants. And we'll give some examples coming up. So with those definitions behind us, we can start to think about a coverage criteria for mutation. The coverage criteria is typically mutation coverage. And mutation coverage is simple, at least conceptually simple. For each mutant in the set of mutants, the test requirement contains exactly one requirement. Have a test that kills that mutant, right? So in the aggregate, the test set must kill every mutant. Or rather, the test set must kill every mutant that's not equivalent, because the equivalent ones can't be killed. So a test kills a mutant if and only if the behavior of the mutant while executing the test is different from the behavior of the ground string or the original program while executing the test. And from this, we can put together a coverage metric. The coverage metric is typically called mutation score, and it's just a measurement of the number of mutants that we've killed divided by the number of mutants that can be killed. So let's look at a couple of mutations and just start to get a little feel for what does a mutation operator do and what does a mutant look like. So here's our original program. Very simple program, max, pass in 2 integers, it returns the larger of the 2 integers. So I might take this program and I might mutate a relational operator, and I'll change if I is greater than or equal to j to if I is less than or equal to j. Well, I have definitely made a mutation. Can I kill this? Is there a test that I can write that'll kill it? Actually, this one's pretty easy, because really what I've done is I've turned max into min. So I could write a test to kill this. I could say assert equals 2, max of 1 and 2. And the original program will return 2. The mutated program will return 1. And by executing this test, I will have killed that mutant. So let's make another mutant. All right, we'll mutate a variable. We'll change return j to return I. Can I kill this mutant? Anybody have a suggestion?
Yes, when j is greater.
When j is greater. Sounds good. All right, so how about we assert equals 2, max of 1 and 2, and our original will return 2, and our mutant will return 1. Great. Let's have another mutation. Here I'm going to replace one of the statements with a trap statement, and a trap statement simply throws an exception, crashes the program whenever that mutation is reached. Well, it's pretty clear I can kill this one, right? Anytime that I is greater than or equal to j, I'm going to reach the trap statement. The program is going to crash, which is different than the original behavior. So not too difficult. Assert equals 2 and max of 2 and 1. And that'll kill it. And in fact, this mutant is also trivial. Test that reaches that mutation will be killed, because every test that reaches the mutation will cause the program to crash. Whereas in the original, the program will not crash. Let's take another one. Let's mutate this relational operator again. We're going to change it from I is greater than or equal to j to I is greater than j. Can I kill this mutant? Any thoughts?
I'll go out on a limb and say no.
No.
I think it will return always correctly.
Because if they're equal, it doesn't really matter which one you return.
Yeah.
Yeah, okay, you've exactly got it. So a test for m. Well, I could try and then pass it in 2 and 1, but it turns out that it'll always return the correct value. So no matter what I do, no matter what test I give it, it will always give me the same results back. And the reason is the only difference in behavior is when I is equal to j, because in the original, when I is equal to j, we'll execute the then, whereas in the modified one, when I is equal to j, we'll execute the else, but I is equal to j. So we return the same value either way. So there's an example of an equivalent mutant, and it's a pretty simple example, but you know, it's I think maybe starts to open your eyes a little bit to, oh, you know, maybe it's not so weird that mutated programs can actually be equivalent. So when we write mutants, we'll often use this notation. We'll write the program here on the right. We'll write the original program, and then we'll add in the mutants as additional lines with these little delta numbers. And the implication is that in mutant number 1, this delta 1 line replaces the previous line. In mutant number 4, this delta 4 line replaces the previous line of the original, right? And so number 3, trap replaces return I. So you'll see this notation a lot, and we'll use it pretty extensively because it's just a nice compact way to denote several mutants without having to write the whole program again and again. And so we'll often refer to these as mutant 1 or delta 1 or M1, and you know, mutant 4, delta 4, M4. Those are all notation that we'll use to refer to that particular mutant. So let's go back and revisit mutation coverage for a moment. So we had a requirement to have a test to kill each mutant. But what does kill really mean? So if we think about the Ripper model, going back to week 2, probably, in the Ripper model, program execution has to reach a fault. The fault must infect the program state with an error. The error must propagate, not most propagate, must propagate to an output. Making myself a note, slide 20. And then the error must be revealed somehow to the tester. And this kind of suggests 2 different definitions for what it means to kill a mutant. So we can think about mutation in terms of strong mutation. Basically, strong mutation means that there's an observable output of the test that is different on the mutant than it is on the original program. In other words, strong mutation requires reachability, infection, propagation, and revealing the error. But we could also think about mutation from a perspective of what we'll call weak mutation. In weak mutation, it's sufficient if I can change the internal state of the mutant. If the internal state of the mutant is different from the internal state of the original program at any point, then I have weakly killed that mutant. So weak mutation only requires that I reach the fault and that the fault infects the internal state with some error. And it doesn't require it to propagate or be revealed. So why are these 2 things interesting? Why are they both interesting? Well, it turns out it's easier to weakly kill a mutant than it is to strongly kill one. And that's not a surprise, right? Because just by definition, anytime I strongly kill a mutant, I've obviously already weakly killed it and then also required that the error propagate and be revealed. So certainly it's no harder to weakly kill than to strongly kill. And in fact, it's usually easier to weakly kill than it is to strongly kill. And some mutants can be weakly killed but can't be strongly killed. And so actually, let's go back to this one for a moment. We called this mutant original. We called this mutant equivalent. We called it equivalent because it always returns the same value as the original. So this mutant cannot be strongly killed, but it actually can be weakly killed, because if I is equal to j, then the original one, the program counter, right, the flow of execution runs to return I, whereas in the mutant, the flow of execution goes to the else. And so we have weakly killed this mutant because the internal state from the perspective of the program counter is different, but we can never strongly kill it because we can never see any behavioral difference in anything that's observable from the outside. So studies have found that tests that weakly kill mutants also tend to strongly kill them, which isn't too much of a surprise. All it requires is that we, weakly kill it and then have propagation and revealing of the error. Weakly killing is easier, but it's much harder to measure, right? It's much harder to write a test that recognizes when something is weakly killed. You have to do a deep internal analysis. You have to be perhaps running it in the debugger and comparing internal state of the program with the internal state of the original, right? It takes a lot of infrastructure and a lot of analysis to determine in actual use if we've weakly killed a mutant. So while researchers tend to like weakly killing because it's a little bit easier to do, practitioners don't tend to like killing weakly very much because it's really hard to recognize when you've done it. So let's look at another weak versus strong example. If we have a function here, is even, it takes an integer and it determines whether that integer is positive, it determines whether the integer is even or odd. So it returns true if it's even, returns false otherwise. So we've got one mutant here where we've changed I equals 0 minus I to I equals 0 plus I. and then we compare I to I divided by 2 times 2. And if I matches I divided by 2 times 2, then we return true, otherwise we return false. So from a week perspective, if we call this with -4, then for the original program, at this point when we execute I equals 0 minus I is equal to 4. For the mutant, I is equal to -4. So consequently, this test succeeds in weakly killing the mutant. But what happens then? Well, whether I is 4 or -4, we do the division, we multiply it by 2, and I is equal to I divided by 2 and multiplied by 2 in both cases. So we return true in both cases. So we are unable to strongly kill this mutant. So all of this takes us to an approach or a concept that we can use to use mutation testing to develop a set of tests. So imagine we have this original program P, that's our ground string, our original artifact. We want to develop a very strong set of tests for P. We can use mutation testing to do that. And what we'll do is we'll take the original and we'll mutate it to produce a set of mutants, M1 through MN. And typically mutation testing is able to produce a lot of mutants. From that set of mutants, we'll select one. Doesn't need to be the first, doesn't necessarily matter which one we select. We're just going to select one. And we're going to try to write a test to kill it. And along the way, we might determine that it's equivalent and that we can't write a test to kill it. Either way, let's assume that it's not equivalent. We'll write a test that kills that mutant, passes on the original, fails on the mutant, we've killed the mutant. Then we need to think about whether we've found an error here. And the error isn't in the fact, whether there's an error in the original program, it's not the killing of the mutant that tells us there's an error in the original program. It's actually what we have learned along the way as developers. As I was examining this mutant, trying to come up with a test case that would kill it, did I discover something about my original program that was incorrect? Right? So it's actually my analysis process in the course of writing a test to kill this mutant, or in the course of analyzing this mutant and determining that it was equivalent. Did I find a defect in my program? And if I did, then I'll modify the program, and then I'll remutate it into a whole new set of mutants, and I'll start the process all over again. If I didn't discover any problem, then I'm going to assess how complete we are. And I'll usually do that by looking at what my mutation score is compared to some mutation score threshold, right? So I might consider, okay, this is my first one. I've killed 1 out of 1,000. Yeah, okay, I'm not very done yet. There's plenty more to do. But perhaps I might decide when I get to 50%, that might be my stopping point, or 75% might be my stopping point. We'll talk a little later about how we might actually come up with a reasonable stopping point, but I'll determine, have I done enough work? Am I satisfied with my test set yet or not? And if I am not satisfied with my test set, then I'm going to select another mutant and I'm going to repeat the process. I'm going to analyze that mutant, consider it, see if I can write a test for it, determine whether I've learned anything along the way that makes me realize, oh, you know, I have a bug in my program. So mutation testing is really a tool to force us to take a very, very close look at what the implementation of our program is. So question in the chat, are there good strategies for knowing how to create a mutant, or is this just something you use your best instinct for? So we'll come back to that. There's actually established tools and established sets of rules that we can use. And in fact, we really need to do this practically. We really need to be able to do this on an automated basis. doing a manual mutation, like we did in the past few examples, that simply doesn't scale very well. So we'll need an automated tool to do this. And fortunately, we have those available. So yeah, the process is extremely labor intensive, right? As you can imagine, creating hundreds or thousands of mutants and going around this loop and analyzing each one and coming up with a test, yeah, that's painful, that's time consuming, that's expensive. If done well, it also results in an extremely strong set of tests. And so, yeah, the outcome is a very strong set of tests. There's an assumption here. The assumption is that the mutation operators that our automated tool is using are well designed, right? If we have good mutation operators that elicit good tests, then the output of this process will be an incredibly strong set of tests, potentially better than every other criterion that we've looked at this semester. So if so much relies on a good mutation operator, what does it mean to be a good mutation operator? What is a good mutation operator? Well, a good mutation operator is one that creates mutants that are somewhat similar to programmer errors. Now, programmers make all kinds of errors, so it's hard to put that in a box and put a bow on it and say, here's the full set of errors that a programmer can make. But making the kinds of errors that programmers make, that's going to lead to good tests. Researchers design lots of mutation operators. And often they then attempt to empirically determine which ones are effective. And what they'll do is they'll try to find mutation operators such that a test that kills a mutant made by that mutation operator also tends to kill mutants that are made by other mutation operators. And if that sounds a little bit like, I feel like there's a definition of subsumption in there somewhere, you're right on. So here are some mutation operators. These are taken from a particular tool for Java. We can have arithmetic operator deletion, arithmetic operator insertion, arithmetic operator replacement, conditional operator deletion, insertion, replacement, logical operator deletion and insertion, logical operator replacement, relational operator replacement, statement deletion, shift operator replacement. This list can go on. But this is kind of a high-level list of some fairly common ones. So let's take a look at what some of these things look like. So an arithmetic operator deletion. I'm going to find each statement in the program everywhere that an arithmetic operator appears, and I'm going to remove that arithmetic operator. Now, most arithmetic operators are binary, like addition. So when I take A equals B plus C, I can't simply remove the operator and have A equals BC, because A equals BC, that can't be compiled, right? I've violated the syntax. So a better version of an arithmetic operator deletion mutation would take the binary operator out and would also take out one of its arguments. And in fact, a better yet version of arithmetic operator deletion would generate two mutants for each binary operator, one taking out the left argument and one taking out the right argument. So by running an AOD, arithmetic operator deletion, mutation operator, on this original line, A equals B plus C, I would get two mutants. I'd get A equals C and I'd get A equals B. We could look at arithmetic operator insertion. Well, there's only so many operators you can insert, right? And again, it's very hard to insert binary operators because now I need another argument, and where am I going to get another argument from? I mean, I suppose you could make one up if you were clever enough and understood which other variables were in scope at the time and things like that. Mutation tools tend not to do that, and so instead they tend to rely on unary operators. So we can insert a unary negation, or we can insert a pre-increment or a post-increment or a pre-decrement or a post-decrement, or we can insert a a bitwise not. So those are unary operators that are pretty easy to insert. We can have arithmetic operator replacement. This one's easy to understand. For every unary operator, I'll replace it with every possible other unary operator. For every binary operator, I'll replace it with every other possible binary operator. So I'll take this A equals B plus C, and I'll turn it into A equals B minus C, A equals B times C, A equals B divided by C, A equals B mod C. I think I'm done. I may have missed something. Conditional operator deletion. Same thing. We can delete unary operators, unary conditional operators like not. We can delete binary operators like and, in which case we also have to delete one or the other or each of the operators, of the operands, excuse me. So in these examples, none of these examples are exhaustive, right? I'm not showing you all of the things that this operator could do with this original program. I'm just showing you a couple examples of what it could do with this original program. In fact, we could have A and B, A and not B, I think are the ones we could make, right? Because we can delete the not, we can delete the and A, we can delete the and not B, so we can get 3 out of this. Conditional operator insertion. As mutant 1 shows, it's fairly easy to insert a unary conditional operator, right? We can insert a not easily enough. Makes a little less sense to insert binary conditional operators, but we can do that too. So we can insert or true or false, and true and false, XOR true, XOR false. We can do conditional operator replacement. Just take that whole condition. Replace the operator with something else, right? Replace and with or, replace it with XOR, or take the whole thing out and replace it with true or replace it with false. Logical operators, I think you're starting to get the idea. I don't want to beat you up too badly over it by going through every one. Relational operators, right? I can change less than to greater than, or greater than or equal to, or less than or equal to, or not equal to. I can replace it with true or false. Statement deletion. Statement deletion is an interesting operator that can delete a statement or part of a statement. So here, given this, if A and B, then C equals true, it can delete the entire thing, which is what it's doing in mutant 3, or it can delete the condition, as it's doing in mutant 1, or it can delete what gets executed if it's true, as it's doing in mutant 2. So we can delete all of a statement or parts of a statement. Shift operator replacement, pretty straightforward, although the first time I looked at this, I was like, triple shift? What the heck is that? Actually, not something that's run into very commonly, but I think triple right shift in Java retains the leading bit, retains the sign bit, whereas a regular shift right does not. So back to mutation score. We started talking earlier about what mutation score was, how I might use it as a threshold, how many mutants have I killed versus how many mutants are there, or more correctly, versus how many mutants are there that can be killed. So here's the formula for mutation score. The number of mutants I've killed divided by the number of total mutants minus the number of mutants that are equivalent. But I have a serious problem here. I don't know how many mutants are equivalent. And I can't know how many mutants are equivalent until I've evaluated all of the mutants. And as a result, I can never really know the mutation score for real, the actual mutation score. I can't know what the mutation score is at any point until I'm actually done. Because until I'm done, I don't know what that denominator is. So this is a serious problem because it prevents you from setting any kind of threshold. Well, I'll stop when I get to 80%. All right, well, that sounds reasonable, but how do you even know when you're at 80%? And the fact is you don't. So quick summary coming out of this. We can use mutation testing for two different but related things. We can use it to develop sets of tests. We can also use it to evaluate sets of tests. And it occurs to me I didn't really have a slide that talked about how to use it to evaluate sets of tests. But what we're doing there for evaluation, let's say I take a program and I write a set of tests on it using statement coverage. Sorry, I'll use the terms of the class, node coverage. I write a set of tests using node coverage. And then I write another set of tests using edge pair coverage. Well, how well do those compare? Well, what I can do is compare both of them to mutation testing and say, well, if I run the set of tests from node coverage, how many mutants does it kill? And if I run the set of tests from edge pair coverage, how many mutants does that kill? And now I have kind of a standard ruler that I can use to determine which of those approaches is better, right? Which of those approaches kills more mutants and by association probably finds more defects. So that's how we use it for evaluation. So mutation testing is very powerful. You can come up with an extremely strong set of tests, but it's very labor intensive and very expensive to do. And consequently, it primarily remains a research tool. There is one tool out there that has a little bit of use in industry. It's called PIT or PI test, pitest.org, I think. And it's used a little bit in practice, but again, not much. All right, so that takes us to the end of our lecture. We're 5:51 now. Let's go ahead, we'll take a 9-minute break and we'll start up again at 6. All right, so I'll see you at 6 o'clock.